Yeah, then if the thing works, we can have Philémon, whose topic I need to read. So it's about SLE and its partition function in multiply connected domains. So it's answering one question about how SLE can be defined in non-simply connected domains. Go ahead.
Yeah, thank you very much to the organizers for the kind invitation. It's a real pleasure to be here and to talk in front of such a nice audience. So yeah, as Evelina said, I'll be talking about SLE and more specifically SLE in multiply connected domains. So yeah, thanks for the question this morning and the advertisements. So this is the joint work with Johanna. We'll try to kind of follow the following plan. So in the first part, I will remind the definition of simply connected domains that also Maurice talked about this morning, and explain how we can then define SLE multiply connected domains as a measure that might not necessarily be finite. And in the second part, I will describe how we can construct these measures more explicitly and address the question of finiteness.
He wants to go to sleep, so you have to be touching.
Okay. Yeah, go through this way. So okay, hopefully it works now. So to remind what SLE is, it's an object that was introduced by Schramm in the early 2000s as a one-parameter family of random curves in simply connected domains of C. So yeah, maybe I'll try now. Okay, sorry about that.
Does you have to go to sleep or is
The thing is the plug.
it's the fun?
I've changed the rules.
Maybe close to the
This one seems.
Yeah, I changed the ports. Maybe this way would work.
Okay, let's see.
Yeah, sorry about that. So, yeah, it's defined in simply connected of C, simply connected domains, but we typically see it as a long curve from 0 to infinity in the upper half plane, and then we can transport these measures by conformal maps. And importantly, these measures, as Maurice said this morning, satisfy two important properties, which are conformal invariance and the Markov property. And these properties are very natural from the point of view of statistical mechanics, and it makes SLE a very good candidate for the scaling limits of interfaces and many observables and discrete models, and actually in a variety of cases, convergent. And yeah, Schramm's argument was that actually these two properties single out measures on curves in a way that one really obtains this one-parameter family of probability measures. Maybe it's good to go through the argument once again. So if we have a curve on the upper half plane, then as Maurice said again this morning, so there's a unique conformal map by the Riemann mapping theorem that sends me from the upper half plane minus this curve back to the upper half plane. The map is normalized in some way, and it sends the tip of the curve to a point here on the real axis, WT, and the map satisfies a differential equation. And so if we believe that this curve should have the Markov property, then given another point along the curve, and conditioning on the section of the curve up to that point gamma s, then we can also map it out using these mapping out functions GS, and end up with a conformal image of the tip of the curve. And now if we believe in the Markov property, then the tip of this curve should be distributed again like an independent SLE. And so when we map it out using another mapping out function G tilde, the tip gets sent to a point W tilde, and the Markov property basically tells me that this W tilde, which is equal to WT minus WS by just following along the conformal maps and using the fact that they're unique, and conditionally on gamma of 0s, this is independent of n equal to gamma t minus s, WT minus s, which shows that W has stationary and independent increments. And the other property that we have is the conformal invariance, And what that means for us is invariance of the law of the curves with respect to maps that fix both the two endpoints, 0 and infinity. And it turns out that this is also one parameter family of maps, which is given by dilations. So in particular, we want our curves to be invariant under some scaling. So we have to change the time, but this is similar to how random motion is invariant under scaling if we are allowed to reparameterize. And so what it tells us once again is that if we start from gamma and map it with GT to some W, and if we do the same thing with dilating gamma by some lambda, then we obtain another point, W tilde. If we believe that these two curves have the same law, then these 2 points should have the same law, and the W tilde is exactly equal to lambda W T over lambda squared, because that's how we dilate the curve here in the first place. So we get that W is scaling invariance. And so these two properties, stationarity and independence of the increments and scaling invariance, imply that Wt has to be a multiple of the Planck motion. So we end up with this one parameter family of laws that are generated when taking this driving function W to be a multiple of the Planck motion. Any questions about this so far? Okay. So now let's see how this goes in multiply connected domains. And imagine that one wants to define a probability measurement curve, joining a point here and maybe another one here. Well, there's a version of the Riemann mapping theorem for multiply connected domains, but there's a bit less freedom in the sense that all multiply connected domains are not conformally equivalent, and actually the map here that will kind of remove this piece of the curve will send me to an annulus that's thinner. In general, different annuli are not conformally equivalent. So actually, we end up with a domain which is not conformally equivalent to the previous one. There is still a Loewner equation through which one can define SLE, but there are two differences. The first one is that there are more sort of parameters to keep track of, because the size of the domain changes along the evolution of the curve, and the relative position and sizes of the holes also changes. And also, if one just plugs in the Brownian motion for this Wt, then this curve in general might not end at a specific point here. It will actually end up at a random points. And since we want to define SLE as a law on curves between 2 points, then it's not exactly the same setup. And the other problem is that now there's only one conformal map from the annulus to itself that fixes 2 points, and this is the identity. Whereas previously it was a whole family of maps given by the dilations. So in some sense, the conformal invariance property is much less stringent, and basically any driving function that is given by Brownian motion multiplied by something non-constant will lead to curves that satisfy these two properties. So we get many more SLE than we had in the first place. So all of this motivates the fact that we need an extra property if we want to end up with a characterization of SLE in multiply connected domains. Earlier in the literature, the case of SLE in the annulus was studied in particular by Dapeng-Jan, who showed that if one also imposes the condition of reversibility, so that an SLE from x to y has the same law as the reversal of an SLE from y to x, then this leads to a unique law on curves. It is specific to the annulus, and in more general multiply connected domains, Lawler suggested using the restriction property, which is what I want to describe now. Okay, so for the restriction property, I should say that it's a property that is highly connected also to conformal field theory. There's been a series of very nice work that study the CFT of the SLE loop measures, so by Lawler and Figo, and also Molina, Xian, and Wong. But I will stick to what I think was the original motivation for studying the restriction property for SLE, which is this question of convergence of the self-avoiding walk to SLE, also into a question that was asked this morning. So self-avoiding walks in the upper half plane is a uniform measure on self-avoiding walks of reverse length n, and they satisfy this interesting property that if one conditions these walks to avoid a compact set K away from 0, then actually one ends up with the law of self-avoiding walks in H minus K, in the sense that this conditioning preserves the uniform distribution. And since it's believed that these self-avoiding walks should have a scaling limit as n goes to infinity, it's natural to ask the question in the continuum, what is the value of kappa such that this SLE kappa would satisfy this restriction property. This question was answered by Lawler, Schramm-Loewner in 2003, and they showed that this value of kappa is actually 8/3. So also, as we've seen this morning, this is why it's conjectured that the scaling limit of self-avoiding walks is SLE 8/3. And they could also show that the probability that an SLE hits or doesn't hit a compact set K can be computed in terms of this functions phi that removes this compact set K. So to rephrase this maybe a bit differently, they showed that the law of SLE 8/3 in H minus K is absolutely continuous with respect to SLE in H, and the random Nicodim derivative doesn't depend on eta, it's just a normalization constant here on the right-hand side. So here the same equation. And actually in the same paper they derived a more general version of the restriction property for all kappa, 0 and 4, which as we've seen this morning is the range of kappa for which the SLE is a simple curve. So they could show that the same thing holds, but now the random Nicodim derivative involves an extra term, which this one depends on the curve eta. Then H and C are quantities that are very much connected to CFT, but for the purposes of this talk, we can just understand them as algebraic expression in kappa. And M is the mass of random loops that intersect both the curve and K. And at this point, maybe it also makes sense to, so SLEs are probability measures, but because we are to compare them in different domains, maybe it makes sense to consider them no longer as probability measures, but actually just as measures of some mass, in the same way that self-avoiding walks is the uniform measure, so we have to normalize by the number of walks of length n, so if we compare to different domains, this is something that might change. And the nice way of doing this is to just absorb this term as being a partition function of that SLE in H minus K, so that for the non-probability measures nu, we end up with this fundamental identity for the restriction property. Any questions about this? Okay. So now I'll just go over how Lawler suggested to use this to define SLE in multiply connected domains, an extra property to characterize SLE. So we are interested in laws on curves joining 2 points in a multiply connected domain, and we require that these measures satisfy the property that we had in the beginning, so conformal invariance and the Markov property. But now we add this extra requirement that comes from the restriction property, which is that our candidate measure, nu d, it has to be such that when restricted to curves staying in a simply connected domain d prime, then this measure has to be absolutely continuous with respect to the SLE measure in d prime, which we know exists. And the random Nicodim derivative is prescribed to be exactly this expression.
This viewpoint requires x and y to be the same.
Same component of the boundary.
Yes.
Thanks. Yeah, that's a very good question. So this definition doesn't depend on where the 2 points are, but we will see that when we actually want to construct these measures and study the finiteness, this will be an important difference. So I'll come to that in a bit. And so a couple of easy consequences of this definition. Well, the first one is actually existence and uniqueness. And the reason is that probably one can think about this condition as being sort of a way of constructing a measure by prescribing its marginals, in this case on simply connected domains. So a kind of Kolmogorov extension argument tells you that there is a way of defining this measure mu d, and it's unique up to multiplicative constants. And it's not a priori a probability measure because these guys here will change the mass, so they're no longer probability measures. So these measures in UD exist, but they are not necessarily finite. But there's one case actually where we can show quite easily that they are finite, which is when kappa is less than 8/3. And the reason is that the restriction property implies that to define this measure mu in an alias, between 2 points on the same boundary, then the law actually has to be absolutely continuous with respect to SLE in the whole disk. And the random derivative has to have this form. And because for kappa less than 8/3, C is less than 0, well, because this is a finite measure, we get that also this has to be a finite measure. But in general, it's not clear a priori that these measures would have finite mass or finite partition function. So it was answered positively by Lawler in 2011 for D anomalous, but left open for the other cases. And maybe another side question is whether there's a more explicit description of these measures, because we've seen that the previous definition is rather non-constructive.
Why does it message the consequence?
So this is because of here we kind of prescribe what the marginals of the measures are in simply connected domains. And so in abstract measure theoretic arguments, kind of like homograph or construction measures via their values on pi system gives existence and uniqueness of the measure.
Okay, you already used the SLE in the simply connected map to construct this.
Yes, yeah, we use here the fact that this measure is unique by Schramm's arguments, essentially. Yeah, and so these are the results that we can obtain. So for different values of kappa, and coming back to the question of Christophe, indeed there's a fundamental difference between the cases when the two endpoints are in the same boundary component or different boundary components for any finitely connected domain. And the reason is that the restriction property asks us to compare the law of SLE with that in simply connected domains. And in that case, the non-crossing case, there are only two types of simply connected domains joining X and Y. There are those that go to the left and those that go to the right. So to construct a measure, we kind of need to construct it separately in these two topological cases. And here in the crossing case, well, the curve can wind around any integer amount of time around this circle, so there are kind of counted many classes of topologically different simply connected domains. So for kappa equals 4, we can construct these conformal restriction SLE in both cases, and finiteness of the mass is a consequence of the fact that we define them through the GFF, which is a probability measure. And for kappa between 8/3 and 4, we can construct them in this non-crossing case, but we don't know how to do it in this crossing case, and I will explain a bit later why it's different. But the main message is perhaps that in both cases, we start from a construction of SLE in simply connected domains that uses other conformally invariant objects, so either the GFF or CLE and Brownham excursions. And we extend these constructions to the multiply connected case by distinguishing on these topological classes of the SLE. Any questions? So, on the time that I have left, I'll try to explain in a bit more details this case here of kappa equals 4 and the 2 points on the outer boundary. So the starting point of that connection is the fundamental result by Schramm and Sheffield, which is that if one looks at the Gaussian free field in a unit disk, so now with some specific boundary conditions, constant on one side and also on the other side with the opposite value. The GFF we've seen this morning, and these boundary conditions mean that we have the same covariance function for the GFF, but now the mean is given by the harmonic extension of these boundary values. So Schramm and Sheffield showed that actually there is a curve, which is a deterministic function of the field, and is a level line and satisfies the Markov property in the sense that conditionally on this curve, the GFF splits into a GFF with boundary condition minus lambda, or mean constant equal to minus lambda on the left side of the domain, and an independent GFF with mean plus lambda on the other side. And their theorem is that this curve is actually distributed at SLE4. But maybe what's more interesting to us is not that this curve is SLE4, but that we can check the restriction property leveraging the connection with the GFF. So that goes as follows. So if we have a compact set K on the boundary, well, we can use the Markov property of the GFF, of this GFF over here, to, depending on its values on the boundary of K, to write it as sort of a new GFF with boundary conditions still plus lambda here, but now random boundary conditions here, which are given by plus lambda plus the restriction of the previous GFF on that boundary. And this is nice because now the thing which was what led to the level line of the GFF in D restricted to stay in D minus K, we can compare it to the law of the level line in D minus K directly. And basically, instead of looking at these level lines in different domains, we now look at these level lines for GFFs with different boundary conditions. And this is something that we know how to compare. We can compute the derivative of these level lines, and we can average the randomness of this phi here to ultimately check the restriction property. And in multiply connected domains, so we can try to play the same game. So now we have an extra, we are in the annulus. And here, we have to decide what are the boundary conditions for the GFF. Actually, if we put something that's less than lambda in absolute value, then we can define a level line, but it might hit this inner circle, which is not what we want in order to define a law on curves between x and y. And maybe the most natural choice is to take actually these values to be minus lambda or plus lambda. So if, say, we take plus lambda, well, there is still one bad thing that can happen, which is that the level line is more likely to go to the left, but it can still go to the right somehow. And then this Markov property for the GFF is a bit weird because now we can write it, but like the GFF on the left-hand side, its mean is non-constant and will depend on the position on the curve. So yeah. And on the other hand, if the level line goes to the left, then actually we are in the same position as before, because now we can write the Markov property, and if we remove a compact set K such that we are now in a simply connected domain, then basically the same argument as before in simply connected domains that one changes the boundary conditions of the GFF here will work, and we will be able to check the restriction property. And so because, as we said, ultimately we want to construct these SLE measures on these different topological classes, we can actually just restrict the level line to go to the left. So to summarize, the recipe for the annulus SLE is the following. So we throw a biased coin to decide on the boundary conditions of the GFF, and then we sample a level line that's restricted to go to the correct side, depending on these boundary conditions. So stated in a bit more details, and again here, so this is stated for the annulus, but it works pretty much the same for any finitely connected domain. It's a kind of a mixture of laws of level lines of GFFs, conditions to go into the correct side, and there's a normalization constant here, which tells me how I have to throw my biased coin in the first place. It's given by there are various ways to express this in terms of the modulus, also the annulus. And I'm not sure I have much time left, but yeah, we see that SLE4 is not the level line of a single GFF, but rather a conditioned level line of a GFF in some sense. And I don't have much time to go over this, but basically the way it works is kind of the same. We start with a result from Werner and Wu, which says that this SLE can be constructed as the right boundary of a bunch of Brownian excursions sampled on this arc with some intensity that depends on kappa, and then independent CLE. So by following the right boundary of this, we end up with a curve that has the distribution of SLE kappa. And applying sort of the same recipe of conditioning on the topological events, one can check the restriction property actually much more easily. Again, this works for any finite connected domain, but now the two endpoints have to be on the same side, and the reason is actually perhaps quite simple, is that so if we want to define a Laurent curve joining these 2 points, then the curve will actually split the domain into 2 disconnected pieces. So we can really identify, say, the left part as, and the curve as the right boundary of what we had on the left parts. And on the other hand, if we look at a measure on curves joining these 2 points, then the complement of this curve is still connected. So we cannot really see this as the right boundary of something sampled on its left side. So yeah, that's why this crossing SLE kappa we still don't know how to construct. But in the rest of the cases, we know, and then the partition function is finite. Thank you.